This is a vision of the future. A launch system that will transport ordinary people to the edge of space and back again. This spacecraft will open the universe to all. It's a dream of those who will design and build the next generation of space planes. In the very near future, spaceflight will become an everyday activity. The corridors of space will become as busy as the airways of today. The environment surrounding our Earth will become the largest construction site ever. Dozens of space stations will orbit our planet. These weightless cities will launch and maintain thousands of communication satellites and provide a stepping stone for deep space exploration. A fleet of space planes will transport passengers and cargo quickly and cheaply. As more and more space planes ferry components up from Earth for use in space, we will build larger and more complex space stations, floating gateways to the universe. But the future is already here.
It's amazing what man can do.
I'm in awe.
The awesome power, the noise, the roar.
You give me the chance like that.
This is our first true spaceship, returning from the ultimate journey, a 6 million mile ride around our planet.
Gs, folks. Descending through 76,000 feet at 270 indicated. Have a good HUD. 500.
It's our supreme flying machine, the Space Shuttle. The first ever machine equally at home traveling through the vacuum of space or flying through the Earth's heavy atmosphere.
50 and 250. 30, 25, 15, 10, 5, touch. Speed brake, waiting for 179. 179, arm and deploy. Shoot. Coming. You're rotating.
It has flown over 80 missions and carried over 200 astronauts into space.
Anybody who's got any sense of adventure ought to want to fly the space shuttle. The rocket ride is the best ride you'll ever get in your life. You go all the way around the world every 90 minutes. You get 16 sunrises and 16 sunsets every 24 hours.
20.
Sound suppression water system activated.
15.
Atlas's computer is now controlling.
Yeah, last check was like 3 foot C's, maybe 9.
T-minus 12, 10, 9, 8, 7. We have a go for main engine start. 5, 4, 3, 2, 1, and liftoff.
break free from the Earth's gravity, the shuttle must use giant rockets to propel it to a speed of 17,500 miles per hour, 10 times faster than a bullet. Once in orbit, its engines must operate in an airless void where there is no lift for wings, no oxygen to burn. The shuttle has to protect its crew from the most hostile surroundings ever explored. On its return to Florida, it crashes through the skies 50 miles above Houston. It must shield them from an atmosphere whose friction would burn them to a cinder in seconds. The dream of building a space plane like the shuttle has existed almost since the earliest days of aviation. As far back as 1929, German carmaker Fritz von Opel piloted a rocket-propelled glider nearly 1 mile in a flight that lasted just 75 seconds. It was the birth of the rocket plane.
Fritz von Opel tries out the first rocket plane.
In less than 4 decades, this primitive machine would evolve into an aircraft that could take man to the outer edge of the atmosphere. By 1967, the X-15 was rocketing its pilots to a height of 300,000 feet, almost 60 miles high, halfway to orbit.
That's a good light, that's a good light.
Touching the very edge of space, these pioneers of aviation were almost the first astronauts. But the technology needed for a plane to leave the Earth and return safely was still out of reach. The urgency of the 60s space race demanded a far less subtle approach: massive force. In 1969, NASA celebrated its greatest triumph as it landed a manned spacecraft on the Moon. Even as its astronauts explored the lunar surface, NASA's giant rocket program was already in danger. The giant Saturn V wasn't reusable. The cost of building a new rocket for each mission was simply too great. NASA has continuously experimented with other rocket systems in a quest to find a cheap launch vehicle that could be used over and over again.
8, 7, 6, 5, 4, start check engines.
The future of space planes belongs to the descendants of this, the first reusable rocket craft, the DC-XA. Operated by only a handful of technicians, this test craft is one of a number of designs that have paved the way for routine and affordable space travel. Lifting off under its own power, the DC-XA has no throwaway boosters or stages like conventional rockets. Its unique propulsion system allows it to maneuver and fly in any direction. Constructed from super lightweight materials, almost 90% of its launch weight is fuel. At the end of each flight, this remarkable machine makes a spectacular return, landing on its tail in its original takeoff position. The DCXA has provided vital information in our search for the space plane for the 21st century. Its first successor is Venture Star. Fully reusable, Venture Star will operate like a normal airplane inside the Earth's atmosphere and like a spaceship in orbit. Planned to be operational by the year 2004, Venture Star will begin a new era in commercial space transportation. Fitted with a new system of thermal protection and a new type of propulsion, it will take off and land under its own power. Each craft will have a turnaround time of only 7 days. Best of all, it will operate at 1/10 of the cost of current launch systems. Another design for the 21st century is the mag lifter. It's filled with people and cargo, not fuel. Present launch systems have to carry all their fuel and power with them. With the mag lifter, the fuel can be left on the ground. Future space planes like this will use the incredible power of an electromagnetic field to help them accelerate to launch speed. But for the moment, our only operational spaceplane is the Space Shuttle. Today, there are 4 orbiters in NASA's fleet: Columbia, Discovery, Endeavour, and Atlantis. Each one can be used numerous times. They can't launch on their own, but they can glide back to Earth. NASA's shuttle fleet has flown more than 1 billion miles and has delivered more than 60% of the world's total payloads into orbit. Hundreds of tons of cargo, satellites, and communications equipment. In Earth orbit, you don't feel gravity, so shuttle astronauts can perform experiments impossible on Earth. In this unique, weightless laboratory, scientists, engineers, and doctors have learned how to handle zero gravity. But to fly to its destination in space, this vulnerable spaceplane, no bigger than a small commercial jet, must survive extremes that no aircraft in history has experienced.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
15 monitor air Houston, now controlling. 217-218, interrupt. Roll program, Houston.
There has never been a flying machine that takes the pounding that the orbiter does.
A little Cessna goes from 0 to 150 miles an hour. The space shuttle goes from 0 to Mach 25. You literally sling it to about 18,000 miles an hour. There's some risk associated with that.
Okay, ready. Cabs in, risers down, CO2 on. Start with a shake of your life here.
Waiting to be blasted into space, the astronauts in their small spaceplane are sitting on the most powerful rockets on Earth. When the main engines fire up, searingly hot gases explode at more than 8,000 miles per hour. They are so powerful, they create giant acoustic shock waves. The vibration caused by the noise is enough to shake the shuttle apart. To dampen these acoustic shock waves, at the exact moment the engines reach full thrust, 300,000 gallons of water are released into a trench below the shuttle. vapor cloud and exhaust fumes blow out more than 2 miles in either direction. As the shuttle accelerates, it pushes through the dense air so fast that massive stresses build up on its light aluminum frame. To prevent it from disintegrating, the main engines are throttled back until the shuttle reaches thinner air in the upper atmosphere. When the pressure reduces, the shuttle begins accelerating again, rocketing towards space at 15,000 miles per hour. After discarding its solid rocket boosters, the 3 main engines power the shuttle the remaining 50 miles into orbit.
Endeavour Houston, go with throttle up. Roger, go with throttle up.
Once the external liquid fuel tank is jettisoned, this fragile machine and its crew have survived the first leg of a fantastic journey.
Welcome to space, guys. Thank you.
Time on orbit is very expensive, and so your day is packed. But if you do get a little spare time, what came to me anyway is I'm looking down on the Earth and I'm looking out the window at this black void of space and the harsh environment that we're in. What I hear in the background is the cabin fans of the vehicle. Everything is just running smoothly, and I'm thinking, what a fantastic spaceship to work so well. You don't think about what it's protecting you from.
In order to survive the extreme conditions of space, a spaceplane must create a microenvironment in which both humans and machinery can function. As the astronauts go about their tasks, a life support system automatically provides everything they need to survive. Onboard filters and air conditioners control temperature, humidity, and air pressure. An atmosphere identical to that on the Earth is produced and completely replaced every 7 minutes. The orbiter must also power its huge banks of electronics and computers. Over a 2-week mission, onboard hydrogen fuel cells generate as much energy as 10,000 car batteries. A byproduct of these mini power stations is large quantities of pure water. The crew drinks some of the water, but the rest has to be jettisoned. It spews harmlessly out into the freezing vacuum of space, where it drifts away as tiny particles of ice. The shuttle must also carry the power to maneuver itself in this weightless environment. It is equipped with 44 small thruster rockets in clusters around the nose and tail. They produce tiny amounts of thrust, but in space there is no friction, no resistance. This small ejection of gas is enough to give the shuttle a powerful kick. But this propulsion system is also highly sensitive. Firing its thrusters in short bursts, the shuttle can move forward or backward and turn 1 inch at a time.
Current distance is 104 feet.
This remarkable precision enabled the shuttle to rendezvous and connect with the giant Russian Mir space station as they both sped over the Earth at 18,000 miles per hour. This spectacular meeting was not just a publicity stunt. It moved us one step closer to the building of the next generation of space stations, in which we will live and work. But this wasn't the only instance when the shuttle's intricate docking abilities have been put to the test. Its most spectacular mission was as a breakdown truck to capture and repair the stricken Hubble Space Telescope. Once it has completed its mission in orbit, the shuttle must survive its toughest test, a return journey of over 12,000 miles in less than 1 hour. To begin its perilous journey back home, the shuttle first must slow down. With one large burst of thrust, the shuttle drops into a lower orbit. It's on its way home. With no engines to regain height, there's no turning back. The shuttle is positioned nose up, ready for re-entry. The crew has just 30 minutes before they hit the upper atmosphere and encounter a wall of fire.
What the orbiter has to go through is unlike anything that's asked of any other flying machine.
Your feet are literally in the pilot's seat a few inches, or not much more, from 3,000 degrees or close to it.
It's like trying to fly a normal airplane through the middle of a volcano and have it come out of the other side in one piece.
Ever since the beginning of manned spaceflight, the danger of re-entry has been a constant problem. The underside of early capsules used in the Mercury and Apollo programs were covered in a thick, heat-resistant resin. This protective layer was designed to burn and break away, providing just enough protection for the crew to survive re-entry. But for a reusable spaceplane to be a success, we need a reusable heat shield. For the shuttles to survive up to 100 re-entries, they're covered in a layer called the thermal protection system. Early wind tunnel tests showed that during re-entry, the temperature would vary enormously across the orbiter's surfaces, requiring a different type of protection for each area. Captured by infrared cameras during a night landing, the nose cone and leading edges of the wings were seen to glow at temperatures hotter than molten lava. To resist these extremes, these surfaces are made of a solid block of reinforced carbon, capable of withstanding temperatures of 3,000 degrees. The upper surfaces of the fuselage don't experience such high temperatures. They're covered in soft cloth blankets made from 90% glass. Handmade in a sewing shop at NASA, over 2,000 blankets are used on each orbiter. But it's the belly of the shuttle that is the largest area in need of special protection, provided by over 25,000 silica tiles. No two tiles are alike. Each one is designed and measured to fit exactly the contour of the shuttle skin. One by one, the tiles are painstakingly glued into position. This special silicon-based adhesive remains flexible from 0 to 3,000 degrees. If it became too brittle, the tiles would break off. These tiles are so efficient at removing heat that they can be taken from an oven at 2,000 degrees and held by bare hands after only a few seconds. In the first shuttle flight, a few of these tiles fell off. It caused some damage, but the shuttle got safely back to Earth. Each tile weighs just a few ounces and has a soft, foam-like structure inside. This fragile outer skin of tiles and blankets is all the shuttle has to protect it through its fiery return to Earth. The shuttle drops from a height of 120 miles down to 75 miles, where it slams into the atmosphere at nearly 16,000 miles per hour. The crew is strapped into their seats, in pressurized suits, just in case anything goes wrong. Outside, just a few feet away, their machine begins to take the ultimate punishment. As the space plane screams down into the thicker atmosphere, it collides with trillions and trillions of tiny gas molecules. It hits them so hard that it creates a glowing plasma of electrically charged gas particles around the shuttle.
And I can see the plasma just building and collapsing in a bright white flash down the middle of the vehicle.
This plasma is crazy.
It's like little pieces of vehicle flying off in front of us there.
Within the plasma, the shuttle is traveling in a fireball as hot as the surface of the sun. To survive re-entry, the orbiter must slow down even more. It utilizes the drag of the upper atmosphere to reduce its speed by flying a series of giant S-shaped turns. 20 minutes from touchdown, the friction on the shuttle's skin reaches maximum, scorching the protective tiles to 3,000 degrees Fahrenheit. When it finally emerges from its fiery cocoon, the shuttle is on the final leg of its journey. Still over 500 miles from the runway, it will cover this distance in less than 10 minutes.
Gs, folks. Descending through 76,000 feet at 270 indicated.
Have a good HUD.
As the shuttle's computers sense an increase in external air pressure, they transfer flight control from the thrusters to the wings. As the wings bite into the dense air, the space plane becomes an airplane.
45,000 feet. Range 23 miles.
Without any power from its engines, the orbiter glides to Earth at 3,000 miles per hour. It's still traveling faster than the speed of sound, and 2 sonic booms are triggered by shock waves from the nose and wings.
Central Florida got a wake-up call.
Approach and land.
The shuttle is descending 20 times faster than a conventional aircraft. "5 minutes before touchdown, the commander takes over from the computers. They train for hundreds of hours for this single moment.
5 minutes. Copy.
The orbiter hits the runway at over 200 miles per hour. The space plane has returned home. The shuttle program is by far NASA's longest commitment to manned flight. It is the world's most successful spacecraft, but the road to orbit was far from smooth. "4 years after the last astronauts left the moon, NASA unveiled the space shuttle. "10 years of design and 2 years of construction had gone into building it, and it had cost $20 billion. This was the first space vehicle designed to carry both a crew and a payload into orbit and fly back again. NASA hoped the shuttle would change space exploration forever, it did. The shuttle's unique design combined 3 systems in one to ensure maximum reusability. First was a delta-winged spaceplane, the Orbiter. With built-in rocket engines, it could carry a maximum of 8 crew and over 30 tons of cargo. The Orbiter weighs 100 tons and is the same length as a DC-9 airplane. The second component of the shuttle system was a giant external liquid fuel tank. Containing 500,000 gallons of liquid propellant to feed the orbiter's engines, this fuel tank would be the only component of the shuttle that would be destroyed during launch. But the orbiter's engines weren't sufficiently powerful to launch this monster into space on their own. It needed the third system, a pair of solid rocket boosters, mounted either side of the liquid fuel tank. Their enormous thrust would lift the entire 2,000-ton package off the launch pad. These 3 elements had never been tested together. The shuttle's first flight could be its last. It was crewed by 2 men, Commander John Young, NASA's most experienced astronaut, and first-time space flyer Bob Crippen. On April 12, 1981, the world held its breath for the maiden voyage of Space Shuttle Columbia. This was to be the first time a new launch vehicle had been tested with men on board.
Toward the White Room, in which they will be prepared for entry into the orbiter. T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start. Liftoff of America's first space shuttle. And the shuttle has cleared the tower.
Speeding into space, Columbia carried the hopes for the space program. The shuttle was to prove so successful that even America's biggest rival in space decided to copy it. This is the Soviet shuttle. Its name is Buran, meaning blizzard. Buran was developed in the early 1980s to give the USSR its own spaceplane. It contained design concepts almost identical to NASA's shuttle. Its designers later admitted borrowing the American blueprints. Buran was designed to be launched simply as a payload. It strapped to the side of the world's most powerful rocket, the giant Energie. In 1988, Buran made its first and only flight. After completing this faultless test flight in 3 hours, Buran touched down to the cheers of the Soviet Space Administration. Unmanned, Buran had orbited twice around the world. Its whole mission had been entirely controlled by computers. With the breakup of the Soviet Union and a cash-strapped Russian economy, the project has been shelved. Once the pride of its space program, Russia's spaceplane Buran is going nowhere. But it had proved that computers, as well as astronauts, can command the world's future spaceplanes.
When I first started flying, it was sticks and cables and pulleys and things, and then you get to this thing and you're totally dependent upon the computers, and so you just have to put your trust and confidence in them. You have to. You have no choice. I mean, everything depends on those computers.
Launch day, and another flight of NASA's spaceplane is about to begin. As the liftoff approaches, 3 miles away in a reinforced bunker called the firing room, more than 300 engineers and technicians are preparing themselves for the most critical moment of the mission.
The orbiter is literally loaded with liquid oxygen and hydrogen potential explosions, and it's an extremely dynamic situation for us. There are hundreds and hundreds of things that must be monitored, hundreds of things that could go wrong. We have to know extensive information about each and every system on board.
With 20 seconds remaining to liftoff, the launch becomes too complex for humans to handle.
T-minus 15 seconds. 12, 11, 10, 9, 8. We have a go for engine start. 3.
As it fires its main engines, deep in the bowels of the world's most complex machine, the shuttle's computers make over 4 million decisions every second. The destiny of the crew is totally dependent on whether those decisions are right or wrong.
Booster ignition and liftoff of Endeavour in pursuit of a Japanese satellite.
Roger, roll, Endeavour.
The shuttle is designed to operate at the very limits of performance. Without its computers, this highly unstable spaceplane would lose control in seconds and crash. Computers must fly it from launch to landing with absolute precision. Although well over 20 years old, the shuttle's computer systems are even now unequaled in complexity and reliability. Each orbiter carries 5 identical computers. They're responsible for the simultaneous control of millions of components.
One of the most remarkable things about the shuttle is that in addition to monitoring all of the systems on board the shuttle for normal operation, simultaneously it has to consider literally an infinite number of scenarios that might occur in the face of failures or unexpected events, and take the right action with split-second accuracy for every one of those situations. It has to do it right every time because you don't get a second chance.
During every moment of the orbiter's journey, over 10 million sensors and instruments located throughout its structure are feeding its computers vital flight information along 2,000 miles of wires. Ruthlessly searching for errors, any problems they detect are dealt with in a most unusual fashion. Like an electronic jury, its computers discuss the problem, then vote for the best solution. The computers collaborate and solve life-threatening problems before the crew even know they exist.
25.
Standing by to activate the sound suppression water system.
15.
T-minus 10, 9, 8, 7. Go for main engine start. 3 main engines up and burning. 3. We have a cutoff.
In over 80 flights, there have been only 5 aborted launches, where the computers shut off the main engines with less than 3 seconds to lift off.
No MPS fire detectors tripped.
Orbiter access arm now back in position. Discovery is now in the safe configuration. Crew is in no danger.
The computers have worked perfectly every time. Successful space exploration depends upon an obsession with safety.
There is no error that's acceptable. There's no room for error. There's no opportunity for failure that we can allow with the software on shuttle missions. Human lives depend on it.
The hands those lives depend on are those of more than 300 specialist programmers who spend 3 years creating instructions unique to each mission. Symbol by symbol, character by character, these programmers write more than 420,000 lines of numbers and letters that will control the shuttle during every second of its mission. They are creating an electronic brain. With the lives of the crew at stake, there is no room for error. to make sure it's foolproof. The code is put through the most rigorous testing process in the world. Creating every problem imaginable, the entire mission is rehearsed by the computers more than 10 times before it even takes place.
We have a go for engine start. 5, 4, 3, 2, booster ignition and liftoff.
But once the computers have ignited the solid rocket boosters, there's no turning back. No other machine on Earth possesses quite so much muscle. In order to lift off, the space shuttle uses 2 systems of propulsion, its twin solid rocket boosters and 3 liquid rocket engines located in the orbiter. Designed to last for 55 flights, the 3 main engines built into the orbiter are the only reusable liquid rockets ever built. Compact and lightweight, they are the most powerful and sophisticated rocket engines of their size.
Pound for pound, these engines are extremely powerful. Of course, they need to be powerful if you're going to kick an orbiter into low Earth orbit in 8.5 minutes.
Fueled by a mixture of liquid hydrogen and liquid oxygen, each engine develops over 12 million horsepower, more power than 64,000 V8 car engines. To achieve this power, they must operate at extremes of temperature and pressure.
When we ignite this engine, what you're seeing is probably one of the most dramatic cold starts of any engine in the world.
Prior to ignition, this engine is literally frozen by liquid hydrogen. As the engine fires, its temperature instantly jumps from below 0 to 6,000 degrees, and it reaches full power in just 1/1000th of a second. But these rockets provide only 1/4 of the shuttle's total thrust. Just feet away from the astronaut's cabin are the most powerful rockets in the world, the solid rocket boosters. Standing as high as the Washington Monument, they are loaded with 500 tons of dry rocket fuel. In less than 2 minutes, they rocket the shuttle to an altitude of 30 miles at 9 times the speed of sound. But the amazing power of solid rockets has one disadvantage. Once started, they can't be stopped, as the crew of Challenger discovered on January 28, 1986.
21 seconds. Solid rocket.
It was the worst accident in NASA's history.
9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Control, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles. Engines throttling up. 3 engines now at 104%.
Challenger, go at throttle up.
Challenger, go at throttle up.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Man's finest machine had failed. But how?
Flight GC, we've had negative contact, lost downlink.
Soon after liftoff, the right solid rocket booster developed a serious leak of red-hot gases from its lower joint. A bright flame can be seen licking the side of its external tank. As the flight continued, the gases burned away the booster's lower strut, eventually causing it to tilt into and puncture the external tank. 500,000 gallons of hydrogen ignited in a giant fireball. But it wasn't the explosion that killed the Challenger crew. The tiny compartment containing the crew remained intact, clearly visible as it plummeted to the ocean beneath. Many experts believe that inside, some of the crew were still conscious until the fatal impact with the water, over 2 minutes later. NASA recovered slowly from the tragedy. After taking the remaining fleet out of service for 2 years, it redesigned the solid boosters and developed new escape systems and safety drills. In more than 50 missions since Challenger's tragic loss, there have been no further problems. But man's most amazing machine still has one major problem. It's getting old and out of date.
The shuttle is a beautiful machine. It does everything we ask it to do, but it was designed in the 70s and has old technology and is very expensive. It's got an external tank that we throw away every time. It's got solid rocket motors that need to be refurbed every time. It takes a lot of people, a lot of infrastructure to go do that.
As we move toward the year 2000, our current generation of space planes faces a serious problem. They consume huge amounts of money. They are pricing themselves out of business. Maintaining NASA's fleet of 4 shuttles requires the full-time attention of nearly 30,000 people. It costs several $100 million to send each astronaut into space. The cost of just one launch has been estimated at $1 billion. So the race is on to design and build a far more cost-effective launch system. The need to have a fleet of commercial space planes is greater than ever before. As we consume and demand more and more information, faster and cheaper space planes are needed to deliver thousands of satellites into orbit. A new breed of spaceplane is already on the way. The Japanese space agency, NASDA, is developing a small spaceplane called HOPE. Designed to ferry astronauts and cargo to the International Space Station, HOPE could be in operation early next century. The French have a different concept. Named Hermes, their spaceplane is designed to be launched on top of an Ariane 5 rocket. Carrying up to 4 tons in payload, Hermes will carry astronauts and materials to and from the International Space Station. The future is within our grasp.
What we're trying to do is take advantage of technology and have a vehicle that flies more like an airplane, that you take off and land, you don't have to throw things away, you don't have to refurb it as much. It takes advantage of things that we've learned for the last 25 years. If we do that, we can have greater access to space, explore the universe, and do some really great science.
In the foreseeable future, space planes will be a part of everyday life. But what will their destinations be? Some will literally be super-fast transporters to other countries. Traveling at a height of 70 miles, spaceplane passengers will fly from New York to Tokyo in 30 minutes. Others will dock at the International Space Station, already under construction. As fleets of spaceplanes bring equipment and materials from Earth, we will build new space stations for future travelers. Ordinary citizens will travel to luxury hotels and orbiting universities. When the problems of prolonged weightlessness on the human body have been solved, a new breed of spacefarers will commute daily into orbit. A later generation of spaceplanes will even allow us to voyage to manned bases on the moon. And one day, spaceplanes will provide the springboard for deep space exploration. Man's most extreme machine will have turned his most extreme dreams into reality.